This PowerPoint is to accompany the carboxylic acids and esters topic. It's just part one of the topic. We're going to look at properties of carboxylic acids in this PowerPoint. Ideally, you do need to print the booklet off to work in. It's on Connect under the Module 6 tab, which is the Organic Chemistry and Analysis module for Year 13. If you can't do that, don't worry. Still use this PowerPoint as a basis for your learning and make your own notes, and we can sort out your booklet when we return to college. So as I say, this is just for part one, where we're going to look at the properties of carboxylic acids. The textbook reference then is page 463 to 465, and as usual, as you work through this topic, do pause for reflection when suggested to process what you're learning. And if you need help or clarification at any point, then email your tutor or indeed ask questions when you get onto Teams. Okay then, let's make a start. So you've met the carboxylic acids before in Year 12. If you remember then, the functional group looks like this. So C double bond O, OH. And shown with the displayed formula, you can see it follows our usual rules where carbon makes 4 bonds, oxygen makes 2, and hydrogen makes 1. So the functional group is called the carboxylic acid functional group, sometimes also referred to as the carboxyl group. So we'll have a go at drawing and naming now. If you do need more practice on this, there is another PowerPoint on Connect called Carboxylic Acids if you do want to have a bit more practice. So we'll do the first one together. Question A is butanoic acid. So if you remember from your our UPAC nomenclature system, the but then means you've got 4 carbons, and the oic acid tells you that you've got that carboxylic acid functional group. So looking at that drawn out using displayed formula then, remember that this one would be carbon number 1. Okay, you could also have a go at drawing it using skeletal formula. So if I have carbon number 1 here, so 1, 2, 3, 4, and then to get the functional group, we'd have double bond O, and then the bond going to the OH. Okay, so you could also do structural formula. So CH3, CH2, CH2, COOH, butanoic acid. So have a go now at questions B and C, and then you can click onto the next slide to go through the answers when you're ready. Okay, so you might want to pause at this point, have a go at question B and C, and then we'll go through those together. Question B, propanoic acid. The end of the name, oic acid, tells you that it's a carboxylic acid. The beginning of the name comes from the parent alkane, which is propane. We've replaced the E with the oic acid. So prop, remember, is 3 carbons. So using displayed formula, it will look like this, where this carbon here is carbon number 1. To use skeletal formula, we'd go 1, 2, 3, and then to get that functional group on, double bond O, and then the OH. Okay, I hope that you can draw it a lot neater than me, but hopefully that makes sense. Make sure the bond does go to the oxygen, not the hydrogen. All right, the next one then, a little bit longer. Again, the end of the name shows that it's a carboxylic acid functional group, oic acid. So it used to be pentane. We chop the E off and we replace it with oic acid. But it's not just pentane, it has a methyl group on carbon number 2. So the displayed formula would look like this. Well, actually that wouldn't be fully displayed So be careful in the exam. You would have to display all the hydrogens separately to not lose the mark. But as before, this would be carbon number 1. Okay, and to draw that skeletally then, we'd go 1, 2, 3, 4, 5. So here's our functional group on position number 1. Okay. And then carbon number 2, we'd have our methyl group. So when you are naming and drawing carboxylic acids, the most important thing to remember is the C of the C double bond O, OH is carbon number 1. Questions D and E are asking us to name the following carboxylic acids. If you haven't done this already, just pause the PowerPoint or video and try to answer those questions and then press play to check your answers. Okay, let's have a look at compound D. So as always, you're looking for the longest continuous chain of carbons. So if we look at that one being carbon number 1 and we count from right to left, we can either have 4 going straight across, but remember you should always check out those branches. If you go up to that one, that still gives you 4 carbons. We check out this one, that would only give you 3. Okay, so we do need to start from the point that that's carbon number 1, and our longest chain here is consists of 4 carbons. So our parent alkane would be butane. We chop the E off and end it with oic acid, so we've got butanoic acid. But we've also got some branches or some alkyl groups. So if we go with our green route, this means we have a methyl group on carbon number 2 and a methyl group on carbon number 3. So there's 2 methyl groups, so we'd say dimethyl. And remember, you need a number for each one. So if we put all that together, that gives us our name, 2,3-dimethyl butanoic acid. So just remember convention, we put commas between the numbers and we put a dash between any numbers and the word. So 2,3-dimethyl butanoic acid for compound D. Okie dokie, let's have a look at E. Well, again, we're looking for the longest continuous chain of carbons. So if we start here, we can go straight across the molecule and that will give us 6 carbons. So our parent alkane name is hexane. Now it's not just hexane because on carbons 1 and 6 we have our carboxylic acid functional groups, and there are 2 of them. So instead of it just being oic acid, we have dioic acid. Now systematically we would say the dioic acids are on carbons 1 and 6, but because we know that they need to be on carbon 1 or at the end of the chain, then those numbers aren't needed. So if the question in the exam though does say give the systematic name, you are probably safer to include that 1 and 6 in with the name. With dioic acids, the convention is slightly different. We don't chop the E off, so we keep the parent alkane name, and that gives us our final name, which is hexane dioic acid. So systematically, it would have been hexane 1,6-dioic acid. Okay, we can also deduce the general formula for a carboxylic acid. If we look at just question D, where there's just one carboxylic acid group, so if there's just one acid group, we would call it a monobasic acid, mono meaning one. Without that carboxylic acid group, it would have been like an alkane. And if you remember, the general formula for an alkane was CnH2n plus 2. So if we replace one of those hydrogens with the carboxylic acid functional group, you end up with CnH2n plus 1, and then the COOH. So if you've printed off the booklet, we're on page 3 now in your notes. Just a few questions to get you thinking about the properties of carboxylic acids. So when we say it's an organic acid, that's because they contain carbon. We can also describe them as weak acids. Just pause. Can you remember the definition for a weak acid? Okay, so a weak acid, remember an acid is a proton donor, or you could say that it releases H+ ions in solution. Now, if it's a weak acid, then it won't do that 100%. We only get partial dissociation. So if we put those facts together, a good definition here is that it's a proton donor that only partially dissociates in aqueous solutions. So always think of those two words when defining what a weak acid is. If that was a strong acid, you'd change partially to fully. Now we can show that happening by use of an equation. If we use an example here of butanoic acid, we can show that partial dissociation by using the equilibrium sign. So the equilibrium sign we've met before. So on the left you've got the butanoic acid, on the right you can see that the H has gone. Now the line here isn't the covalent bond, that's the charge, because what's actually happened is that OH bond has broken. Both of those electrons from the bond have gone to the oxygen atom. So what type of bond fission is that? If you were thinking heterolytic bond fission, you were right. Okay, both electrons have gone to the oxygen. So hydrogen has lost an electron, so it's now come off as a H+ ion, or we call it a proton, because literally that's all it is. And that electron that used to belong to hydrogen has now gone to the oxygen. So that's why we've got that negative charge. Now, generically, that species now on the right-hand side is, is called a carboxylate ion. It's an anion because it's negatively charged, but carboxylate ion is the C double bond O, O minus. Specifically because it came from butanoic acid, we now call it the butanoate ion. So the oic acid has changed to O8 ion. Okay, so have a go now at writing an equation to show the dissociation of another one. So this time we've got 2-methyl pentanoic acid, so good practice for your nomenclature. So draw out the acid and then what it would look like after that partial dissociation. Pause the video or PowerPoint and try that now. Okay, so you should have drawn something like this. So on the left, we've got the carboxylic acid group. And if we remember then our name, so if this one is carbon number 1, you've got 5 carbons in the chain there. And then you've got that methyl group on carbon number 2. Now, do be careful if the question asked you to use fully displayed, you'd have to display all those hydrogens there. So we've used the equilibrium sign to show that partial dissociation, okay, and then on the right hand side you've got the carboxylate ion there, that proton has been released. So instead of it being 2-methyl pentanoic acid, you've now got 2-methyl pentanoate, or the 2-methyl pentanoate ion, okay. So, weak acids then. If you think about pH, you know back from GCSE, pH is the measure of acidity of an acid. If you've got a strong acid, you're looking at a pH of around 1. For a weak acid, you're looking at a pH of around 3, 4, 5, possibly even 6. Okay, so we will be studying how to calculate pH later in the course. but it's that H plus that's responsible for that acidic behaviour. So before we go to look at more detail about the properties of carboxylic acids and then how they react, let's just remind ourselves how we make a carboxylic acid in the first place. So your task here is to describe the synthetic route that could be used to convert ethene into ethanoic acid. Include equations and reaction conditions in your answer. So pause now and try to answer this question. If you get stuck, use the flowchart or synthetic routes map from your organic synthesis notes from module 4. When you're ready, press play again and we'll go through your answer. Okay, so you're asked to convert ethene into ethanoic acid. So you need to think here about what's changing. So spot the difference. If we look at the beginning of the name, eth and eth, then we've got 2 carbons involved in both cases. Now, when we get into year 13, we will be teaching you how to increase that carbon chain length. So you do need to be aware of that. But at the moment, it's just the functional group here that we're changing. So we're going from an alkene to a carboxylic acid. So then you need to think, well, could you do this in one step? Do you know a reaction that can convert directly an alkene into a carboxylic acid? And the answer there is no. So we know it's going to take more than one step. So we're looking at possibly 2 steps here, maybe even more, but typically you're looking at 2 steps at this level. So we're looking for an intermediate. The best way to look now is to focus on the target molecule. So your target molecule is ethanoic acid, that's the carboxylic acid, and think about how you can make that. So the only way we know so far to make a carboxylic acid is from a primary alcohol. So now we've got our intermediate because we know that we can also make a primary alcohol from the alkene. So we're going to go from an alkene to a primary alcohol to a carboxylic acid. That will be your synthetic route. Now, to answer the question, we need to give equations and reaction conditions. I would suggest it's useful to just map out the summary first of all so that you know where you're going with it. And so here we've got the overall route. We can see it's 2 steps, ethene to ethanol, and then the second step there is ethanol to ethanoic acid. Okay, so let's look at the 2 steps individually then, going from the ethene to ethanol. It's a hydration reaction. The reagent here is steam. So if we put H2O, it's really important that we put the gaseous state symbol there as well. We also need a catalyst, and the catalyst is concentrated phosphoric acid. So do remember to put that conc on there too. Here's your equation. So for any organic reactions, it's convention to show the structure of the organic molecules because really you want to see how that functional group has changed. So we can see there the alkene has changed to a primary alcohol. It's an electrophilic addition reaction. We've got 2 reactants joining together to make one product, one desired product, so we've got 100% atom economy. So far so good for sustainability. So now we've got our ethanol, we can convert that by oxidation to ethanoic acid. Now, even though we could do this, technically speaking, at room temperature in the lab, the technique to use here for the ideal conditions is reflux. So reflux allows us to heat it up. It's that continual evaporation and condensation of the reaction mixture so that we don't lose those volatiles into the lab and we get a better yield. So our reflux then is our technique that provides the heat for the reaction. The reagents then, well, it's going to be our ethanol, and we need our oxidizing agent, which is the potassium dichromate. And remember, that won't work unless we have the concentrated sulfuric acid to go with it. So our reaction conditions would be reflux, and you'd also give that catalyst as well. Now remember, for the equation, we don't use the potassium dichromate in the equation. We use an oxygen in square brackets to represent that oxidizing agent. So remember, oxidation is the removal of hydrogen and or the addition of oxygen. And if we go from an alcohol to the carboxylic acid, we will have done both of those things. So for every 1 mole of primary alcohol, we'll need 2 moles of the oxidizing agent. So we can see there that first O will have taken off the 2 hydrogens. So remember to put your water there on the right hand side to balance that equation. So we've done everything the question has asked us. We've described the synthetic route, we've included equations and reaction conditions, so we should get full marks for that. Okay, so back to properties of carboxylic acids then. So we've seen how they can behave as weak organic acids with our equilibrium sign showing the partial dissociation of the H+ ions. Now we're going to look at solubility in water. So why do you think carboxylic acids are generally soluble in water? Just have a pause and think. Well, hopefully you've remembered that between water molecules there are hydrogen bonds, and for a substance to be soluble in water, that substance needs to make hydrogen bonds with the water. So carboxylic acids can do that. They are able to form hydrogen bonds with the water molecules, so they can kind of sneak in between those water molecules and hide out, so it can dissolve. Okay, so a typical exam question would be to draw a labelled diagram to show this. And, you know, a key word here is labelled, so don't forget to put your label on as well. So we're going to look at butanoic acid, why it's soluble in water. So could you do a label diagram to show the butanoic acid forming hydrogen bonds or hydrogen bond with water? So why not give that a go? Just pause and see if you can sketch that out, and we'll come back to it to check in a moment. Okay, so remember this is a technical diagram, and really your thinking needs to start with the definition of a hydrogen bond. So a hydrogen bond, remember, is an intermolecular force. It's the force of attraction between a partially positive hydrogen atom on one molecule and the lone pair on a highly electronegative atom such as NO or F on another molecule. So if you remember that definition, that should help you to draw a good diagram. So if we've got butanoic acid then, so you'll notice on the butanoic acid, we've marked our partial charges because the oxygen here is more electronegative than the hydrogen. So we've created a permanent dipole here. So we've now got our slightly positive hydrogen atom on one molecule. So this is interacting with the water, so the water's underneath, the H2O. We know that's a polar molecule because it has permanent dipoles that don't cancel due to the molecule not being symmetrical, that bond angle of 104.5. So it's important that you, again, write on there those partial charges. So we've got our slightly negative oxygen atom there because, again, that oxygen is more electronegative than those hydrogens. So our hydrogen bond definition then, it's that force of attraction between the partially positive hydrogen on one molecule and the lone pair on the highly electronegative atom on the other molecule. So you do need that lone pair there, and that dotted line goes between the lone pair and the hydrogen. And then don't forget it is labelled, so going back to the question here, that label then, you need to point to that and call that the hydrogen bond. Okay, so because the acid can do that, it makes it soluble in water. Hopefully though, you've been thinking about this oxygen up here as well. This oxygen is more electronegative than this carbon, so there will also be a permanent dipole here. And of course, this oxygen will also have lone pairs. So actually, that C double bond O could also be part of a hydrogen bond, if you will, with water. You could have the lone pair from this oxygen here interacting with a partially positive hydrogen from the water. Okay, but it's more common to draw it as it is on the screen here, with the OH from the carboxylic acid being the one that's interacting with the oxygen from the water. Okay, so just showing you the mark scheme there. If this was an exam question for 3 marks, you'd have a mark for your lone pairs, a mark for the dipoles, and a mark for the label. So do always put all the dipoles on. I'd even be tempted to put the partially positive carbon and the partially negative oxygen from the C double bond O as well, just to be sure. So in the exam, you might be asked to explain why a carboxylic acid can be soluble, but you may also be asked about a comparison between different carboxylic acids. So for example here, butanoic acid we say is soluble, but the solubility of carboxylic acids decreases with an increase in carbon chain length. So why do you think that is? Just pause, have a think. So hopefully you've been thinking about the nature of the hydrocarbon chain length. Because it's non-polar, it can't form hydrogen bonds with the water. They can, however, just form induced dipole-dipole or London forces with each other. So you might want to pause and make a note of that. So when we're looking at solubility of carboxylic acids, it really depends on 2 factors, 2 things. Firstly, you're looking at the number of carboxylic acid groups and therefore the number of hydrogen bonds that could be formed. So previously you've seen a monobasic carboxylic acid, and we saw the hexane 1,6 dicarboxylic acid as well, dioic acid. So the number of COOH groups will influence the solubility. The other thing that influences it are the number of carbons in the chain. So again, pause and make a note of that. So here's a question then to finish off. Why is ethane dioic acid more soluble in water than pentanoic acid? So have a think first of all, and then we can write down a model answer together so you've got that for reference in your notes. Okay, so we can compare first of all the number of carboxylic acid groups. We can say that ethane dioic acid has 2 COOH groups, and so it can form more hydrogen bonds than pentanoic acid. Then we compare the second factor, which is the length of the hydrocarbon section. So pentanoic acid has a longer hydrocarbon chain, which cannot form hydrogen bonds with water, only induced dipole-dipole or London forces with each other. Right, so this is a good point to pause and check progress. So use the learning outcomes on the front cover of your notes if you've printed them. If not, don't worry, I'll display them here. These are directly from your exam board spec. So at this point, you should be able to explain the water solubility of carboxylic acids in terms of hydrogen bonding. Of course, we've done a little bit more than that already. We've been naming and drawing them. We've been thinking about them acting as weak acids, and that's all useful too. It's going to come in handy for the next bullet point, which is all about describing the reactions of those carboxylic acids with metals and bases. So before we do that one, why not stop and have a little break and then come back when you're refreshed. All right, see you in a moment. If you have the booklet, we're on page 5. You should have a table there to complete to summarise some reactions of these carboxylic acids. Now this is where your revision from last week will really come into its own, because we're going to look at writing equations. You're asked to write the equation for the reaction, naming the organic product, identifying the type of reaction, and giving any relevant observations. And the acid we're going to use each time is ethanoic acid. So think first of all what ethanoic acid looks like. Okay, eth, you've got 2 carbons, so the COOH and then the CH3 attached to that first carbon. So your first reaction then is with just a metal, and the metal we'll use is sodium. So find sodium on the periodic table. Remember it's in group 1, so we know that it will form a 1+ charged ion when it reacts, when it loses that electron. So when metals react with acids, they always make a salt plus hydrogen. So you might remember the mnemonic there, MASH, to help you to remember. So what is a salt? Can you remember the definition? Pause, have a think. Okay, so a salt is a compound formed when the H+ from an acid is replaced with a positive metal ion or the ammonium ion. So if you're asked for that in the exam, always make that definition specific for the acid and the metal ion involved. So here we're going to have the H+ from the ethanoic acid being replaced by the sodium ion. So looking at the equation then, you'll have your ethanoic acid with the sodium, and the ratio there will be 1:1. Because it's a group 1 metal, it forms a 1+ charged ion, and that replaces the H+ like for like. So on the right hand side we've got our products, we've got our salt, and we've got the hydrogen. So do remember, of course, hydrogen is one of our diatomic simple covalent substances, so it's H2, and so to balance that we only need 1/2 mole of that. Okay, so look at your state symbols. AQ for the acid, that's essential. Remember, an acid releases those H+ ions in solution, so it's AQ. The sodium here is solid at standard conditions, and the salt, the ethanoate ion there will dissolve, so those ions will dissociate. That salt is soluble, and then the hydrogen, of course, will be a gas. So remember, use those state symbols to give you a clue for your observation. So just pause and think, what would you see when this reaction was taking place? So you should have been thinking about the sodium dissolving or disappearing. The solid doesn't appear on the right hand side, so the solid is gone. And on the right hand side, the product there, we have a gas. So you would see that by bubbles or fizzing or effervescence if you're being a bit posh. Right, you might also be asked to do an ionic equation. Now, our ionic equations really get to the heart of what's reacting. Now, if you remember what to do here, we separate the AQ, the aqueous substances, into their ions. We leave alone the solids and liquids and gases. It's just the AQ substances that we split up. So really, you'd start by writing that equation again, but just pay attention to the AQ substances and write those in using their ions instead. So here we can see the ethanoate ion appears on both the left and the right hand side. In effect, it hasn't changed. So we call that a spectator ion, and we can get rid of that from our ionic equation. So what we're left with then is the metal reacting with the proton from the acid, and then we have the metal ion in solution and the hydrogen gas being evolved. So naming the organic product then, that's the salt, and I've already alluded to it already with the anion. We remember from earlier on in this PowerPoint, that's the ethanoate ion, so sodium ethanoate will be our salt name. Now, the reaction here is redox. I've kind of revealed the answer here without giving you a chance to work it out. But if indeed you assigned oxidation numbers to all the elements in this equation, you would find that oxidation and reduction was taking place. A quick way to spot that is you have an element here, so the sodium okay, is actually changing into a compound. So that would be an obvious kind of first glance, because we know elements are 0, and then here it would be +1. So the sodium has an increase in oxidation number, the sodium has been oxidised, okay? So something else will have been reduced. So could you spot what else has been reduced? Okay, so the hydrogen, the other obvious change then, we've got the hydrogen in the compound, and that turns into the element. So the hydrogen oxidation number has decreased, so it's reduced, whereas the sodium was oxidised. So it's a redox reaction in total. Our next reaction is with a metal oxide, and the example we'll use here is magnesium oxide. So for all of these reactions, we're going to produce a salt. Now the other product in the equation will depend on what the reactant is with the acid. So previously we had a metal with an acid, we produced salt and hydrogen. Here we've got a metal oxide reacting with the acid, so we're going to produce a salt and something different. So have a think about that. The other thing that matters here is the definition of the salt. Remember, we're replacing the H+ ion from the acid with the positive metal ion. And here we're dealing with a group 2 metal. So remember, we're going to have an Mg2+ charged ion in our salt. So that's not going to be like for like with the H+ from the acid. So there's a ratio to consider here. So have a think, pause the PowerPoint and see if you can come up with the equation, and then press play to check your answer. Okay, so looking at the overall then, that ratio there, 2:1 acid to oxide. And that's because if you look at the formula of the salt to make it work, going right back to when you learnt about ions and cancelling those charges to make the ionic compound, we need 2 of the ethanoate ions to cancel out that Mg2+ charge. So if we need 2 ethanoate ions, we need to start with 2 moles of ethanoic acid. The other product then was water. So the 2 protons from the acid react with the oxygen from the magnesium oxide. And again, your state symbols reveal the observations. Here you've just got one observation, the solid dissolves. Now the next one is for the ionic equation. Remember, that gets to the heart of the matter of what's reacting. So pause again, see if you can come up with the ionic equation. So remember, it's just about the aqueous substances. You rewrite the equation with the AQ substances in the ions to show their ions. And just as previous, we can see we've got a spectator ion here. The ethanoate ion hasn't changed, so we can cancel those down. So the net effect of this reaction is the magnesium oxide has reacted with the 2 protons to produce an Mg2+ charged ion and water. So the name of that salt then, it's magnesium ethanoate, and the type of reaction, well, we've got an acid reacting with a base to make salt plus water, and that generally is called a neutralization reaction. Just to make the point, actually, the salt here, the way it's been written at the moment, it's got the ethanoate before the magnesium. You could have written it the other way around. Okay, so it doesn't matter which order you write them, it's all about the ratio, making sure you've got 1 magnesium and 2 ethanoates. So it didn't matter which way around you did it. Our next reaction then is with an alkali. So what's the definition of an alkali? So an alkali is a water-soluble base. It releases hydroxide ions in solution. So here our example is potassium hydroxide. So we'll have K+ and OH-. So have a go at writing the equation then with ethanoic acid. Okay, we've got a group 1 metal here, potassium, so we're back to 1:1 territory. So the acid and the alkali mix the salt and water. There are no visible observations here, no visible changes. The ionic equation then, remember it's the AQ substances you're going to write out showing the ions. So that's what that would look like. Notice the water doesn't change, but we can see the ions now. If we look on the left and the right, the ethanoate ion hasn't changed, so we can cancel those out. And the other one is the potassium ion, that hasn't changed either. So the net effect then is a proton reacting with the hydroxide ion to make water. And in fact, whenever you've got an acid and an alkali making a salt plus water, the ionic equation will always be this. Okay, so the H plus plus OH minus goes to water is common for all acid-alkali reactions. And again, because we're producing that salt and water, we can call that a neutralization reaction. And the name of our salt this time, potassium ethanoate. Our next reaction then is with a carbonate. So here we're using calcium carbonate as the example. So pause, see if you can write the equation for the reaction. So again, we're back to a group 2 metal, calcium Ca2+. So you've got to think carefully about your ratios. So you're going to need 2 moles of the ethanoic acid for every 1 mole of calcium carbonate. So you've got your salt, calcium ethanoate, and the 2 other products then, when we react a carbonate with an acid, we produce water and CO2. So we've seen this reaction before when we were testing for ions back in module 3. Your 2 observations then, the solid dissolves and you get bubbles of gas. When we look at the ionic equation, remember it's the AQ substances that you're separating into ions. So if you've not done that already, pause and have a go and then click play to check your answer. So the ionic equation then, the ethanoate ions cancel down like we've seen previously because they were spectator ions, giving you an ionic equation like this. So this type of reaction then is important because it's one of the ones you need to remember because it helps us to identify substances. If we want to identify carboxylic acid, we can react it with a carbonate, and if you see bubbles of gas, then that will be evidence that it will be the carboxylic acid. Okay, so this is a test for a carboxylic acid. In this example, the name of the salt then is calcium ethanoate. Page 6 in your notes then, just a diagram to help you to visualise when we test for a carboxylic acid using a carbonate. We can actually go one step further and not only will you observe the bubbles of gas being formed, but we could collect that gas via a delivery tube and we could bubble that through some lime water. And what would happen then is that lime water would go from a clear solution to cloudy. A precipitate would form effectively. So the lime water would go cloudy, and that would tell you that the CO2 is being produced. Okay, so the test for a carboxylic acid is to react it with a carbonate. And if you see those bubbles of gas, you can be pretty sure it's the carboxylic acid. And if you want to confirm that gas is CO2, you could bubble it through lime water and the lime water would go from clear to cloudy. Okay, so the carbonate test then is important because that can help us to distinguish carboxylic acids from other weak acids. Now, the other weak acids that we're looking at here are phenols and alcohols. Now, we might not have thought of an alcohol as being acidic before, but they have got the potential to release that proton. So they are technically, they can be technically described as being acidic. They're just not as strong as carboxylic acids, which in themselves are classed as weak acids. Okay, so let's have a look at this table then. There's a lot of information here to process, so let's go through. If we look at the first row, we can see we've got 3 different types of organic compounds. So the first one is our carboxylic acid. We're familiar now with that functional group. The phenol then looks like this. We're going to meet that later in the course, but you can see it's an OH directly attached to a benzene ring. And then finally, the alcohol, it's just the OH attached to a carbon. So what we're saying here is that these hydrogens that I'm highlighting, they can all be released as H+ ions in solution, but the carboxylic acids have a greater tendency to do that, more than phenol, and then phenol more than the alcohol. So effectively you can consider these 3 as all having acidic behaviour, but the carboxylic acids are the stronger acids out of the 3, and the alcohol would be the weakest one. And that hierarchy, that difference, gives us a way in to be able to distinguish between them when we look at the reactivity with different reagents. So looking down the first column now, we can see sodium. Sodium will react with all 3 of those types of compounds, so sodium wouldn't be any good to help us to distinguish between them, but we know a metal will react with an acid to produce a salt plus hydrogen. Sodium hydroxide, notice that it won't react with the alcohol, so that's a good little bit of information. It would react with the carboxylic acid and the phenol, and you should be able to do balanced equations for those. We'll look at phenol later in the course. We'll look at the last one, sodium carbonate. Here's where it really helps us out for our carboxylic acid. Carbonates are bases. Now, sodium carbonate is a weak base, but it will react with the carboxylic acid because the carboxylic acid is a strong enough weak acid for it to react. Phenol, because it's a weaker acid than carboxylic acid, it won't react with the carbonate, and neither will the alcohol. So if you've got an exam question, let's say, and you know that you've got 3 unknown organic compounds, and you know that one of them is a carboxylic acid, one is a phenol, and one is an alcohol, if you test all 3 of them with the carbonate, the one that fizzes or bubbles, that's going to be your carboxylic acid. Okay, so this table is going to come in handy throughout module 6. So we've got it in the notes, but I also suggest that you make a flashcard with that on, or some kind of little poster that you can have separate to your notes so that you can use that for quick reference, because you are going to have to know that information on the table. Okay, so make a flashcard. Right then, that's the end of part 1. So as usual, check your progress using your learning outcomes on the front cover of your notes. So you've just been describing the reactions in aqueous conditions of carboxylic acids with metals and bases. So we've included carbonates, metal oxides and alkalis. Make use of your textbook as well, or on Caboodle. Remember the pages there, 463 to 465, if you do want to read anything just to consolidate your knowledge. Now you have got some practice questions to have a go at, and if you click on to the next slide of the PowerPoint, they'll go through. You can click on to reveal the answers there to check you're working out. So at this point, review your progress, have a go at those practice questions, and then check your answers. If you are getting them right, then that's brilliant. If you're not, see if you can identify any mistakes, and if you need any help, then do email your tutor to ask for help, or you can always ask for help on the Teams session as well. Okie dokie, so that's the end of part 1. The next PowerPoint or video will be about part 2, and it's all about making esters. We've met that already, but we're going to take it a little stage further, as you'd expect. Okie dokie. All right, have fun with those practice questions. See you soon. Bye bye.